Today, on how it's made. Jaws of life. Artificial Christmas trees. Soda crackers. And ratchets. The jaws of life were first used in 1963 to free race car drivers from car crashes. It was so big it had to be suspended from the back of a pickup truck. Today, it weighs as little as 15 kilograms and is small enough for one person to operate. It can free an accident victim from a car in minutes. In an emergency situation, timing is everything. A rescue tool has to pry open a vehicle as easily as a tin can, or cut through solid steel like butter, because a few seconds can make all the difference. What gives the cutting blades and the spreading arms their power is hydraulic fluid. The jaws of life begin with a milling machine that shapes the spreader arms from a bar of solid, aircraft-grade aluminum. The spreader arms then get a protective coating. A lathe now makes the cap that fits on the end of the tool. A high-speed carbide tip shapes the solid aluminum into a finished end cap that is then drilled and treated to a coat of rust-resistant protection. Arms that both cut and spread are made from tool steel. A surface grinder ensures the two arms are perfectly flat. A worker installs a seal that prevents the hydraulic fluid from leaking out of the cylinder. He lubricates a piston with hydraulic fluid so it slides into the cylinder without damaging the interior. Then he taps it in so it will connect with a link assembly. He attaches a link assembly to the piston and secures it in place. The link assembly relays power to the cutting blades or spreader arms. He then attaches an assembled end cap to the cylinder and bolts it in place. He connects the two hoses that lead to the tool's hydraulic cylinder. He puts on a hand grip that protects the hoses and makes it easier to work the thumb wheel. He tightens the bolts and completes the control valve. He then attaches the front handle that allows the operator to hold the tool safely. This protective guard will keep all the moving components away from a rescuer's hands. Then he aligns the holes in the blades to the tool and inserts a steel pivot pin. He puts on a lock nut and, as with all the fasteners on the rescue tool, he tightens it to a precise engineering specification. After mounting the blades, he secures them to the link assembly with a steel alloy pin and a snap ring. Then he folds the protective guard back and finishes assembling the tool. A worker then tests the tool, which has been filled with fire-resistant hydraulic fluid. The fixture he uses is designed to measure the pressure at the strongest point in the cutting. The tool passes the pressure test. Whether it's a rescue tool that cuts through metal or pries it open, emergency response teams arriving on an accident scene will have what it takes to help save lives. The quest for the perfect tree is a rite of the holiday season. Ever since the late 19th century, people have been trying to come up with an artificial version. First, there were feather trees, and later, trees made of animal bristles. But by the 1960s, the use of synthetics finally gave us the perfect fake fir. Today's faux firs can be several stories tall, big enough for your town square. You can get them with many of the trimmings, so decorating isn't such a stretch. These big artificial trees start with a steel skeleton. Rollers bend steel tubing into arcs. They'll be joined to form the base of the framework. Workers weld vertical supports to the arcs, building the structure in sections. A spray of polyester powder gives the welded metal a smooth finish that's actually tougher than paint. They bake the parts to set the coating. After a quick cooling, it's time to assemble all the pieces. They fasten the structure together with U-bolts and a ratchet. Meanwhile, a roll of green PVC plastic winds its way towards a roller equipped with many circular cutters. They slice it into 10-centimeter wide strips. Each of the narrow plastic strips then goes under a roller with even more blades. They shred it into a needle-like configuration, leaving a solid spine at the center to hold the simulated needles together. An automated spool then winds up the fringed green PVC. These artificial needles come in an assortment of colors, so if you want glitz, you can really go out on a limb. Here, streams of the fringed green and a strip of brown PVC travel over tension control guides. Steel wire unwinds and merges with the green and brown PVC. This machine twists them together. The brown strip lands at the core of the twisted fringe, creating the illusion of a stem among the needles. This twisting technology churns out a continuous supply of artificial greenery. Giant scissors slice it to the correct length. To make branches that appear snow-tipped, this machine twists and then frosts the PVC needles with a spray of white latex paint. They use this ring fastener to crimp the artificial foliage together, branch by branch. This creates a tightly knit mass of greenery that will be used to cover the tree's framework. They apply single garlands on key parts of the tree grid first, using a handheld pneumatic fastener. They fill in the sections between them with the assembled branches. This is easier than attaching them to the framework branch by branch. They string the lights and then plug them in to check each bulb. After all, it's easier to change one now than after the tree has been erected, especially since this one will be 1.5 stories tall. They also wire the ornaments to the branches. It's one less job for the customer to do. And now, it's time to put up the tree. They bolt the cone of wired greenery to the lower framework and then hook the panels of artificial greenery onto the rest of the structure. It has taken just one day for this artificial tree to come together, where growing a real one this size would take many years. And the convenience is unreal. Soda crackers are also called saltines, originally a brand name that, over time, became a generic term. You can eat them plain or spread something on them, or crumble them into soup. Doctors even recommend eating soda crackers when you're nauseous, because they're dry and easy to digest. They're flat and bumpy on the outside with a tasty texture resulting from some interesting chemical reactions. Workers first dump ice into a trough to prevent the dough from overheating during fermentation. The first ingredient is a specific amount of finished dough to kickstart the fermentation of this new batch. To that, they add water, wheat flour, yeast, and enzymes to help the fermentation. A mixer blends the ingredients for about 5 minutes. They let the dough sit for 16 hours while the enzymes break down the starch in the wheat into simple sugars. The yeast then reacts with those sugars, producing carbon dioxide gas, which makes the dough rise. They adjust the fermented dough's pH level with sodium bicarbonate to produce the right flavor, color, and shelf life. Then, for additional flavoring, some salt, malted barley flour, and vegetable oil. The mixer remixes the dough for about 5 minutes to blend in these new ingredients. Now they let the dough ferment for another 6 hours. The sodium bicarbonate counteracts the acidity this produces and relaxes the gluten so that the dough now breaks easily when stretched, the perfect consistency for soda crackers. A machine then extrudes the mass of dough into a sheet that's 5 centimeters thick and folds the sheet over itself 3 times. This folding creates the light and flaky layers inside the cracker. The dough sheet then goes through a series of rollers that reduce it to its final thickness, about 1 millimeter. A revolving die cuts the cracker shapes, perforations and all. The little pins puncture the dough and push it firmly onto the conveyor belt. This keeps the dough from deforming when moisture and gases escape during the baking process. From there, the sheet passes under a shower of salt. The sheet now takes a 3-minute trip through a long oven with different temperature zones. Gas flames bake the dough from both above and below. The heat transforms the sodium bicarbonate in the dough into carbon dioxide gas, which then breaks through and escapes. This drives out trapped moisture and forms blisters in the crackers. As the sheet of baked crackers exits the oven, a roller breaks it into rows. The rows then run from one conveyor belt to the next, stacking like roof shingles. Alignment wheels keep them straight until the next set of wheels gently breaks the rows into individual crackers. Each row makes its way through a series of gates that guide it onto a track that leads to the packaging equipment. The crackers are upright now, and the machine begins dividing them according to the number of crackers per package. In this case, those little 2-cracker packs you often get with soup. The cracker pairs enter the wrapping machine, which sandwiches them between a sheet of printed plastic film. A wheel then simultaneously seals and cuts the wrapper between each pair. This all happens at an astonishing rate of 525 packages per minute. And that's the way the cracker crumbles. Ratchets come in many shapes and sizes and can tackle almost any job. Ratchets with socket attachments deliver more power and speed without slipping or damaging the bolt or nut. Just snap an interchangeable socket onto the ratchet and you're ready to get the job done quickly and properly. Versatile and easy to use, a ratchet tightens or loosens nuts and bolts in a continuous motion. It uses removable sockets that fit many different sizes of fittings and fasteners. To start, a steel bar travels into a shearing machine that cuts it into specific lengths. These pieces, called billets, will be used to make the ratchet. A machine feeds the billets into an induction coil, which heats them to about 1,000 degrees Celsius. A forge press then shapes the soft billets into ratchets. The first die creates the ratchet's general form. The second die gives it its finished shape. And the third die cuts off excess metal. The ratchets exit the forge press and fall into a collection box where they cool. Then, a vertical milling machine prepares the body cavity to receive the internal working parts of the ratchet, called the gear assembly. A worker places the ratchet on a hydraulic press, which stamps the brand name and the on-off indicator on the ratchet's face. A lathe cuts away the rough, forged steel from the handle and trims off the end, making it ready to receive the hand grip. A worker grinds any rough edges off the machined ratchet. Then he crimps each side of the smooth handle so it will hold a rubber hand grip in place. The ratchets now undergo a 3-stage tempering process that hardens and strengthens the metal. Ceramic stones and a chemical solution prepare the ratchets for nickel and chrome plating. A plating machine cleans the ratchets, then treats them to a nickel and trivalent chrome plating. The two platings make the ratchets corrosion resistant and give them a bright cosmetic finish. A worker then lubricates the ratchet cavity, puts in an on-off switch, and a spacer to support additional components. A worker sets a retention ball onto a ratchet gear. Then a punch press locks it in place. Next, they fit a gear mechanism into the cavity, then attach all the internal components that control the movements of the ratchet. Once completed, the gear assembly allows or restricts movement. So, putting the assembly into either the on or off position is all it takes to tighten or loosen a nut or bolt. She then puts a rubber seal onto a cover plate and closes up the ratchet. She makes sure the gear assembly works properly. Finally, this machine friction fits a handle on the Ratchets shaft. Evolving from a steel bar to a finished product in 10 steps, the Ratchets must undergo a final test of strength to prove they meet the highest quality standards. They're used for big and small jobs by handymen and professional mechanics alike.